Good afternoon. Welcome to Krishna's classroom. Let's continue with our journey from Riemann to Lebesgue. We are nearly at the last stage now, and in fact, we have defined last time how one can write the integral of a Lebesgue measurable. Okay, so let us briefly recall what that is, and then go over to consider some of the consequences. Okay, but let me again repeat the various steps that we took in this journey. The first step was to define integral of simple measurable. But this we did by using what? Approximated we approximated such functions by a sequence of and define the limit and define the integral as the limit of the integrals of such functions. And clearly we showed that such approximations are possible. Okay, so this is well defined. Third step was we drop the boundedness, but we consider functions with sets of finite, with support as sets of finite measure. So the third step was bounded function It's not bounded function anymore. Uh, Non-negative measurable functions. Non-negative measurable functions with a support again we used to get a sequence of bounded functions to approximate. And then use the suprema of such functions to define the integral. The next stage is non-negative. Once again, this is important. Once again, non-negative measurable functions. Now the step 3 to approximate such functions by non-negative measurable having support sets of finite measure and then defining the integral and then defining the integral supremum of integrals of approximating functions. Now that is how we come to the deal with non-negative measurable functions. But having done that, we go to the next stage, namely we now drop the assumption that these functions are non-negative. Okay. We write them as the difference of, this we have seen last time. We write them as the difference of two non-negative measurable functions. That is the second. And as the difference of two non-negative if f is a measurable function, course E is measurable. Then we write f plus minus f minus, which we have described in our last lecture. And then use 4 to define integrals of and f minus. And that is possible because they are both non-negative. Further, define integral over E minus. Now this is, each becomes finite, then it is well defined. If each of them is, if one of them is infinite, then again the integral can be given as infinite, plus infinity or minus infinity, depending on which one is going to be. And then if both of them are infinite, then of course the integral is not. So that is there. So this is of course subject to the condition. So we introduced what is called integrability. And that is of course demanding both f plus and f minus. Having a finite input. In the sense this which is equivalent to so that is the final stage. Now I'm repeating this because you should also see how mathematical ideas are systematically developed. Okay. So what you do is you go from one step to the next step by reducing the step. For instance, you have reduced the problem of writing the integral of a measurable function to writing down to finding out the integral of a non-negative measurable. Okay, so that was the reduction. So we had started with the simple functions, bounded measurable functions on sets of finite measure, which was done using simple functions. Then these class of functions were used in the next stage, namely non-negative measurable functions with finite support, and then we used the results there to get the integral, or to go to devise the integral of, once again, non-negative measurable functions, but now dropping that finite support condition. And then eventually from that stage we go to measurable functions by writing them as two non-negative measurable functions. So the general principle is, if you want to solve a problem, reduce the problem, it is possible, to solving problems whose solutions are already available. Okay, and if you read the beautiful book by Polya, G. Polya, which every student and every teacher should read at least once, because this would enable you to follow your thoughts when you solve a problem. In fact, you stand out from the arena of solving the problem in your mind and try to visualize what are the steps. And in fact, through this process, you can often find the path. And one of the important things that you do is to solve a problem for which you do not know the solution, to try to transform it into another problem whose solution you. Okay, so through these steps you can solve the given problem, and this is very important. I mean, this is a very interesting book, very easy to read. You don't need to really spend too much of effort to read this book. It's very lucidly written. One should read this. It just looks into the process that goes on while solving a problem, not only in mathematics, but even any problem that you encounter in your life, the way in which you try to approach to get a solution. This kind of clear thinking would help you. So it will be a great asset for you in your life if you read through this book. Easily available on the net, or even it's a fascinating, which one should. And there are higher versions of this available, written by Polya, but that is not required. At least a basic one would give you a lot of insight, and then every time you start solving a problem or proving a theorem, you systematically analyze the steps. Not just absorb it, but question every step and how you prove each step, stage by stage, how you arrive at the solution. So you can see the Polya's principles playing a role in it. Okay, so that's just sidetracking. Okay. But let me come back now. Now, having done this, so we have now completed more or less the integration process. Now we look at some of the properties of integrable functions. So we have the following theorem. Inferences that we can make. Let f be integrable over a measurable set. Then f is finite almost everywhere on E and integral of over E is equal to integral over E slash E naught of F plus where E naught is contained in E and measure of so for the integral to exist or for a function to be integrable, you don't require the function to be finite everywhere. Over a set of measure 0, over a set of measure 0, the function may be non-finite and still the integral would exist, because you know that is not going to matter, and that's the content of this theorem. So it gives some insight into the function whenever it is integrable. So whenever it is integrable, you can certainly say that except possibly on a set of measure 0, everywhere else the function is finite. So if the function is, as far as the integral is concerned, the function is nearly finite. Okay. So that is the conclusion that you can draw about the nature of the function. One immediate consequence of this. So we can give some estimates of this integral. Because you know that when the function is integrable, you know that mod f is integrable. So we can give some estimations of this. This is called the integral all this I have discussed in detail with proof earlier, but I am just recalling them for just giving a quick vision of what are the things. So let f be a measurable function of suppose there exists a non-negative function measurable function that is integrable over E and dominates f in the sense that in fact it is enough to have almost everywhere. Then f is integrable over E and integral that's a nice estimate for the integral. So this is often, see, given an f which may have a very complicated expression, but it may be possible to see, to find a function g which bounds this in this way, a function which may be measurable and which is also integrable, because this is going to be naturally non-negative function, and if it is also integrable almost everywhere on E, well then f is integrable over E and this integral is bounded by this. So this integral in such cases would give an estimate of this integral. Okay. So that is one of the consequences. Now of course the standard properties of integral do hold, namely integration is a linear operation. Okay, then you have the monotonicity property, and then also what is called the on splits or on separated domains, the union of the integral, the integral over the union would be the sum of the integrals over the separated domains. So these are some of the properties. So we will take the next set of properties named linearity and monotonicity. This we have seen at each stage this property is valid, and we use this to prove in the general situation. So let me just write here let alpha beta integrable for alpha or beta belonging to R, real numbers, the function is integrable, and this is equal to now this is the linearity. Okay. Now you remember that the previous step we had the decision that alpha and beta are non-negative, but that is no more required, and you can write down this and see it's easy to. If left is less than or equal to g, this is monotonicity. Okay. Now the next theorem is on additivity. Of the integral over domains of integration. This property enables you to split the integral over convenient domains. Integral over a domain into integrals over convenient domains. Okay. So let f be integrable on it. Assume A and B are measurable subsets of P such that A intersection M. A and B are measurable, disjoint, subsets of P. Then that means then integral of A union. These are the standard properties of the integral. So that is the splitting of the integral over a domain into integrals over disjoint domains. Now here we have to assume both A and B are measurable sets. So that is absolutely essential, because you cannot assure that all subsets of a measurable sets are measurable. Okay, there may be some subsets which are not measurable. So you have to have this condition. Okay, so these are all very straightforward things that you expect in this case, and it shows that we have got the integral, which is a sensible generalization of the integrals over intervals that we are. Now we go to convergence problems. So we prove the Lebesgue dominated convergence theorem. Let Fn be a sequence of measurable functions on E or a measurable set E. Suppose there exists a function G that is integrable over E, and dominates the sequence Fn in the sense that mod Fn because here you can possibly relax this by demanding this to be true on a set of measure except on a set of measure 0. That means almost everywhere on it. That these are all natural things that you can do. If Fn converges to F pointwise almost everywhere on E, then F is integrable over E and That means the interchange of the limiting process and the integration is possible. So that you can write this integral of fn, limit of this equal to integral of over e of limit of fn. Okay, then like this. And that would lead to this one. So if f is integrable, if fn converges to f and fn is dominated by an integrable function, then this f is also integrable. And you have this particular point-wise, or not, if fn converges to f point-wise, then integral fn converges to integral of f. Now this is the dominated convergence here. And these are all here you are asking the usual convergence problem, that is whether this interchange of these two operations are possible or not. And here it says that it is possible if these conditions are satisfied. Now you can easily see that, and if this condition is not satisfied, then you will be in trouble, as we have seen examples. Okay, because you remember the example that you have seen. The example that we have seen chi n plus 1, the characteristic function of the interval n to n plus 1. What happens? So fn converges to 0 on a pointwise. Now here you see that you don't have this property valid. Why? What is the reason for that? But we don't have a function, an integrable function that dominates Why? Because the only dominating function that you have is the one that takes values, the function is equal to 1 on, because such a function is g equal to 1 on r. Okay. Or say if you are taking the interval 0 to infinity, then this is so. So we can take this interval as on. But you see, g is not integrable. Here g is not integrable. That is why this interchange of the limit won't happen, because you see that this integral is essentially for gn, this is equal to 1, whereas integral of e over f is equal to 0. So that is not true. So the interchange of the integration and the limiting process is not valid for this. The reason is that, see, you need some kind of restrictions. You cannot make this interchange of limit and integration without, freely. That's the point. You need some kind of conditions on these functions. Okay, I think that gives some insight into this kind of problems. So we have developed the concept of integration from Riemann. We have come to a long way. I mean, in several steps, including construction of Lebesgue measure, etc., etc. It's a long path that we have followed with a very satisfactory definition of the vector. And we have explored the properties of this also. Now, what next? So, we ask the following three questions. One, can you characterize the Lebesgue integrable functions on intervals? Because on Riemann integrable functions, we could characterize on intervals. Now, can you do the same thing for integrals over intervals? That's the first question. The second question is more deeper. It says, what is its connection with what is called the antiderivative? To write down an indefinite integral of this, what is its connection with the so-called antiderivative? Can you call it the antiderivative of the given function? Now, this is, in short, we are asking whether, in what form the fundamental theorem of calculus is valid in this case. Okay, and for what kind of functions it is true, or in what form it is valid. Now, we have seen that this question had an answer which was not very satisfactory in the case of Riemann integration. You had all sorts of conditions required to have this connection of integral with being the antiderivative of the given function. Now, we have once again a stage where you have to ask the same question, and we shall see what kind of result would emerge. So, we have these two problems at hand immediately. One is characterization of Lebesgue integrable functions on intervals. Then, what about the so-called fundamental theorem of calculus in this case? So, we'll have a look at this, and I'll just quote a few theorems to give them. This I have already worked out the entire set of this. It's a long process again, justifying each one of the steps which you have to go through. But having done that, then we come to our final question. Do we achieve what we were trying to achieve? What is that? Suppose you construct L1 space, as we did in the case of Riemann integrable functions. Is that going to be? In Riemann integrable functions, we found that it is not complete. We could construct an example, or we could prove that this is not, RAB is not complete. But is the set of Lebesgue integrable functions on the interval AB could be made into a normed linear space? Then do you get completeness? The amazing thing is that we do get it. In fact, far more general results are available. So, in some sense, the path we have traced, the long, laborious path we have traced to develop the integral was worthwhile. We get eventually a complete norm linear space related to, or got out of, what are called the Lebesgue integrable functions. And that, in a way, is a very satisfactory, or justifies all the trouble that we have taken. And this is roughly the moral of or roughly the story that you have to go through in the case of a first course on Lebesgue integration theory. I'll do one or two lectures to highlight the three other points that I made. One is characterization of Lebesgue integrable functions on intervals. Then, what is the form of fundamental theorem of calculus? Or in other words, do you get in some form what you call the integration that we have developed will give you a sort of anti-derivative for a given function. The final question is, do you get a complete space? If we try to construct the replica of RAB with L1, now working with Lebesgue functions. Okay, so that will be all. So I think I'll stop here at the moment, and then all the details are available in my previous set of. I have gone through something like 80 lectures on Lebesgue integration theory. Now I am doing all this, take you to the abstract integration theory. That is the next stage, or going for a further generalization. So far what I have done is a summary of the paths that we have taken from Riemann integral to Lebesgue integration, highlighting the questions that we have addressed at each stage. This is for the sake of clarity of what is going on. So my experience had been that generally measure introduced in a very abstract form, or just introduced through a set of definitions, do not give any insight into how you arrive at. Often you see that every concept is transparent only if you know why such a new idea has come up and what were the efforts taken to do this. So this was our objective. I wanted to make the integration theory, or the Lebesgue integration theory, as transparent as possible. In any book it is available, but unfortunately it does not, it is there in all the books that deal with Lebesgue integration theory, but it does not really highlight the paths that you take, except some books. So each time you make an advance, there is some compelling reason. Unless you understand that reason, you won't understand why you have gone to the next stage. So my point of these lectures had been to enlighten you to the extent possible, or the way in which I have understood this kind of. So let me stop here for the time being, and I will continue with two more possibly lectures, and after that we'll, in a natural way, go for the next level of generalization, and which is possible and leads to abstract integration. Thank you very much. But my advice is, if you want details, go through the set of lectures. It is there listed in a set of 80 lectures, starting from Riemann integral all the way through. Before that, even there is a set of lectures on Riemann integration. There is one whole package on Riemann integration, ending with the shortcomings of Riemann integration. Then there is the second package, which just looks at Riemann integration and its shortcomings, and from there, following the path, how you mend it by introducing the Lebesgue measure, Lebesgue integration, and so on. And the entire thing, including the completeness theorem, has been proved there. So that takes about 80 lectures in all. And then, of course, we are now treading on a new path, namely abstract integration theory. But before we do that, I thought once again it will be a good thing to visit the path we have taken from Riemann integration. That is what we are doing. Two more lectures, I think I will conclude that path and then abstract integration theory. So the material is available. Otherwise, the material is available in Royden, or any book on integration theory would have all these materials. There is a nice book by Rana where he spends one whole chapter on reviewing Riemann integration and probably the shortcuts of Riemann integration to go to the successive sections on Lebesgue integration theory. Thank you very much.